Hello, everyone, and welcome to BrainMap. This seminar series is co-sponsored by the P41 FundNet Center for Mesoscale Mapping housed at the Martinos Center. So I will just hand it over to Dr. Clarissa Cooley to introduce our speaker today. So, Clarissa.
Hi, everyone. Thanks so much for coming on such short notice. It's my great pleasure to introduce our speaker today, Professor Ed Wu. Dr. Wu is the Lam Wu Professor and Chair of Biomedical Engineering at the University of Hong Kong. He obtained his BEng in Electrical Engineering from Tianjin University in 1984 and Master's in Medical Physics from University of Wisconsin-Madison in 1988. And PhD in Radiological Sciences from University of California, Irvine. From 1990 to 2003, Dr. Wu worked in Columbia University, first as an assistant professor and later as an associate professor of radiology and biomedical engineering. His primary research, he moved to University of Hong Kong in 2003. His primary research focus is to develop brain MRI methodologies for probing brain circuits by combining MRI with electrophysiology, behavioral assessment, and emerging neuromodulation approaches such as optogenetics. Dr. Wu is an elected fellow of ISMRM, IEEE, and AIMBE. And Dr. Wu is the Asia Pacific editor at NMR in biomedicine, and also an editorial board member of MRM. Not mentioned in this bio is his really exciting work that he's doing in low field MRI as well, which is the subject of today's talk, and I think we're all very excited to hear about. I'd like to remind the audience to please address any questions using the Q&A box or raise their hands at the end of the talk. Professor Wu, thank you very much for coming today, and the stage is yours.
Thank you, Clarissa, first for arranging this talk at such short notice. We messaged only a few days ago, and thank you all for coming. It's always an honor for me to be back in this place. I try to be here every couple of years, and just talked to Matt. Probably the first time I was here was 8-9 years ago, and when my lab started thinking and planning the ultra low field projects. And it's really an honor here. Another reason is this is the place that many things first in the MRI world has been developed here. So it's also so good to see Leo and also see my former great student Iris, and congratulations, Iris. Look like you are making it here, and they finally let you survive and promoted you to faculty. So best luck to you in the future. So my talk today is about ultra low field, as Clarissa said. I think it's really exciting to talk to this audience to see Clarissa and Matt, and unfortunately Larry is not here. And so I think I want to kind of talk very quickly, maybe save more time for the Q&A discussion that will not be recorded. He promised me, right? So ultra low field, just kind of some of you say you've been studied rodents. Where does thing come from? Actually, before I studied rodents, I spent a long time at Columbia. At time building the 5T from ground up, right? Basically made a console, gradient coil, to work on the 3D pad funded by NIH Javis Jacob grant under the leadership of Dr. Sadak Helal. Right? He's really a visionary clinician. And then subsequently, we work on the 5T, mainly with the motivation of doing sodium-23 imaging, particularly intracellular sodium in the brain, because he's a neuroradiologist. He's interested in tumor. So we want to know whether or not we can detect the cell death instantaneously by monitoring the sodium-potassium pump. Because once it fails, we see rapid rise of intracellular sodium level. I thought this would be, if I have a high field system, this is where I'm gonna go back, right? And after that, I moved to the animal imaging. Had the fortune of working with many students, such as Iris here. We've been kind of see how far we can push in terms of combining the high resolution bold, low resolution bold function MRI with a bunch of other methods to study the sensory system mostly, not the cognition, right? Actually, I give a talk here before the pandemic, that was my topic. So, but today's my topic is really about how can we have a simplified MRI scanner, right? I think that is affordable, patient-centric, and computing powered, because nowadays our ability to compute is really unrivaled in history, right? It's just keep growing. Yeah. And so I'd like to start with this famous paper everyone knows, and you probably noticed this paper was published exactly 5 decades ago, half century ago, right? So it's a good time to ask, say, in another 20 years in my lifetime, what the MRI should be, right? And you know, I think a lot of members did ChatGPT ask what it's like. I think some of the pictures coming from here, I took from the internet. On the left side, you see this over classical thinking, right? Supercon magnet that lead us donut shaped, and we can make it prettier. On the other hand, on the other side, show this a patient-centric imaging system, basically embedded in the healthcare system, right? So we're going to be, say, in 10, 20 years. I can only ask that question, maybe, especially Clarissa, you can even ask longer questions. I couldn't imagine, right? So, and for MRI, I think is such a wonder. I think it's listed as one of the most useful technological intervention in the healthcare for the last century, right? I remember it made down to the top of the list in one of the papers. Because it's non-invasive and because it's non-ionizing, because it's multi-parametric, intrinsically quantitative. Those traits actually made it perfect hardware platform for future AI-driven diagnosis, even image-free AI-driven diagnosis, right? Provide we are not replaced by CT in 20 years. CT catching up very fast because it's simple, it's fast. They are very focused. And clinically, nevertheless, it's really, I think this is a life-saving technology. Over 200 million MRI procedures are performed every year worldwide. You know, this is my favorite slides. However, but there's only around 75. I would say if you count those uncounted ones in mainland China, maybe there's around 100,000 MRI scanners worldwide only. In comparison, over 200,000 CTs, right? And probably over 2 million ultrasound scanners, right? So, and most of those MRI scanners are concentrated in centralized imaging facility and the radiology department, right? And 90% of them, needless to say, are really located in the wealthy countries. If you plot the MRI demographics, it matches the distributions of McDonald's, right? So how do we get out of this dilemma? I think it's just like many of us sitting here, you know, our ambition, our vision is to see we can develop ultra low field, ultra low power, compact, easy to operate, permanent magnet-based MRI. Because by using permanent magnet-based MRI, we can make the hardware really simple, right? So over the years, I think it's, you know, those are the papers we're all familiar with. I think that, you know, I would say, Matt, really, you wrote the very first paper, right? That was probably the earliest, and using your, you know, by developing this 6.5 millitesla, right? That's quite a few years ahead before we catching up with the ultra low field. And then subsequently, I think Clarissa and Larry had this very elegant, you know, compact, light head scanner magnet, and subsequently you develop into a system demonstrating those big pole images, right? Meanwhile, we've been working on this for a while, and we didn't really publish because we think, you know, MRI is such an old thing. We should finish the project, do the clinical efficacy demonstration, right? And then run the MD, do the ROC curve, then publish. Till one day we saw the Clarissa's paper in the archive. I say, whoa, you have an editor. Once you publish that, basically our paper will have no novelty. So we wrap up everything. We published in the Natural Communication in the December 2000, exactly two years ago, and become probably the most downloaded paper in Nature.com that year. I think it's downloaded 50,000 times. Yeah. So subsequently, in parallel, there are also a group from Leiden, I think Andrew Webb's group, and then of course we all heard about the group from Connecticut, right? And Matt is at least used to be a big part of it, called a Hyperfine, right? So now the movement, I think the movement is going on, but in recent years, I think the my lab's focus is mainly on the computing, because originally when I started, I said nothing really new in MRI. We used to have an ultra low field, right? So we want to build a platform we can acquire noisy but quality data, so we can play with deep learning, right? So we actually started that 3 years ago, finally, and we got some kind of nice, interesting results. That's the main reason I want to share today, right? So if we have this kind of capability, we can actually really develop a new class of MRI scanners, right? It's probably will look like a more patient-centric and more as a point care device, just like ultrasound, right? So here, so what is the real challenge? I think everyone knows the formula here. The challenge here, the key challenge here is signal. We know signal is proportional roughly to field strength squared. That's why we are so hungry for high field, right? And the SNR, if you factor the low field, the coil sensitivity issues, roughly to the field to the power of say 7/4, right? So what does this mean? This means, say, if at the 3T and the SNR, say if you go from 3T to 0.05 Tesla, the SNR dropped by 1,003 times. So what does this imply? This implies if you carry on a 3T scan with isotropic to say 1.5 millimeter resolution, right? It takes 2 minutes. If you rely on simple averaging to mitigate the signal SNR problem, you have to average it for 6.5 years. So that's why we don't want to go to an ultra low field, right? But there's another group of people for many years playing with the Earth field. So they got some signals. So we were very inspired. I think there's hope. So if we can overcome this problem, this will give us a lot of opportunity. Say point of care system that is very, very simple. It's just a device for healthcare. We can use it even for molecular imaging, for research, right? And this will, but however, how do we mitigate this SNR problem? I think here we can go back to the classical engineering. We can boost the SNR signal, say the signal to noise ratio by reducing the coil noise, right? How? Well, why coil noise matter? Because at the ultra low field, the MRI signal, the noise is dominated by the thermal noise from the coil, not the body, unlike at a high field. So therefore, for example, if we can cool the traditional LC resonance circuit, make it superconducting, we can have very high Q coils, right? So we can suppress the noise, right? So I think that we all know Bruker Biosp made a fortune by developing this, right? That is their best product because it's really useful. I'm about to spend $2 million just for that probe, right? Because it increased signal by a factor of 3 without increasing the magnet size. But nevertheless, this may not applicable to ultra low field. The reason is that if you have a coil with such a high Q, your acquisition bandwidth at 2 megahertz, if you have a Q even 100, you only have 20 kilohertz. 20 kilohertz bandwidth will kill some very important sequence, something called echoplanar imaging, which is, I think, is really the cornerstone of a good DWI, right? So maybe who knows? Material people may one day figure out the material, they can reduce the noise by a factor of 10, right? Yeah, I won't be surprised. That's a field rapidly evolving. And secondly, I think we can optimize data acquisition sequence. There's plenty of room there. For example, if you compare the 3T, versus the 1.5T versus say 50 millitesla, look what has been changing. The T1 reduced by a factor of, say, for example here, from say for the gray matter, the T1 reduced from 1.3 seconds to say this around 100 milliseconds, reduced by a factor of 10 almost, right? Reduced to say 300, right? So that means it's reduced by a factor of 4, right? And that means we can rapidly excite the spins, and we at least get SNR 4 there, right? So, but that's not enough, okay? This is why it's still, say, without any, say, post-processing, just using the analytical traditional method, we can actually gain some signal back, right? So, but even that, it would not allow us to to get rid of this number eventually, if we want to have the same image quality, right? So we have to rely on computing. And here I want to give it just to quickly go through two examples what computing can help us in terms of eliminating IF shielding for MRI, in the case of MRI. So the MRI become truly portable, right? So the MRI, we can hold the patient's hands when they are scanning rather than everybody out, right? And the second example is that, well, how can we deploy deep learning? This is also Matt's favorite playground, okay? And how can we use deep learning image formation to mitigate the noise problem, the artifact problem, so that we can create beautiful images, just like a high field. So Tyler would like it, right? Yeah. And so that, because we don't want to give the different looking images to clinician. And because once a well-accomplished person told me, he said he really knows the doctors. He said once you drive a good car, you never want to go back to drive a lousy car. Yeah, right? And you have to give them something, right? Don't tell them it's cheap, it's easy, right? Yeah. So how do we mitigate? First example, I want to talk about, say, the IF EMI removal, right? And I think this is the area Clarissa has been working, I think, made this a beautiful algorithm called the editor, and so that we can, we can eliminate those those negative disadvantages of the bulky IF shielding room, make it mobile, make it more patient friendly, make it low cost, right? So how do we do that? I think it's the idea, actually, once it's all disclosed, published, is relatively easy to understand if you have the engineering background. Say, for example, we have, say, if we have the radio frequency sources here, for example, here, this is the MRI signal source, and this is the environmental EMI electromagnetic interference sources, say, for example, due to an anesthesia machine, right? So this is the MRI receive coil. Typically, if we collect the signal, and then it will collect both NMR signal and the EMI signal, right? And we know, and mathematically, if you go back to the rudimentary signal processing, the signal detected here is related to the source here simply by time domain convolution and the frequency domain additive multiplication, right? So that means if we put another two coils here, we can write down those equations. And if we ensure those EMI sensing coils don't receive any MRI signals, then therefore you can see we can use the historical data, okay, or use some other data to establish the relationship between the EMI signal received by those sensing coils and the signals received by the MR receive coil, right? Then we can go back retrospectively, subtract it, right? So that's the idea. I think this is really, I think, to me, I saw this is a really, when I first time got it, I saw gee, this is incredible. Why it's so simple, right? Why we didn't really think about this, right? And well, I think the Clarissa's group, I think here really did really early using the transfer function here, and then later on come up with this the editor method that forces us to publish quickly, right? And in my group, we try the transfer function, it works. But then we actually believe maybe in long term, we need a deep learning based method to establish this relationship. We think this type of EMI cancellation maybe would be more robust in reality, because the EMI in reality very diverse. It's not generated by a single signal. The source can move around, people move around the scanner to influence the transfer function. So we spent quite a bit of time to come up with a new method to make this truly applicable in reality. And so this is the scanner we actually custom built around 6 years ago. Once it arrived, it has a cage. Then we remove the cage, and how do we? By the way, this scanner is 0.05 Tesla. It looks very dumb and simple. And because we actually just designed the magnet and had the specification, we just put in those standard PCI and etc. The console, we jam this box, it still works. So, but the only difference is that the magnetic material here is samarium cobalt. The reason is that this material is less sensitive to temperature. It's 1 order magnitude insensitive than the traditional neodymium ferrite boron, right? Which is used by most prominent MRI system. So how do we eliminate the EMI here? So this we'll see. During the scanning, we actually position some EMI sensing coils in the environment, including inside electronic cabinets where the gradient amplifier is extremely noisy. Right. So, and during the data acquisition, we have 2 acquisition windows. And the first one is that during the MRI, say this is a 3D fast spin echo sequence. Whenever we acquire MRI data using the MRI main coil, we simultaneously sample the signal detected by the EMI sensing coil here. But during the dead period, where there's no MRI signal, we also do simultaneous sensing. And then what we do is that we use the data acquired during the EMI signal characterization window in absence of MRI signal here. Okay, we use this data to train a simple 5-layer CNN model to do what? So that we can use the sensing coil signal here to predict the EMI signal in the main receive coil. Once we establish this model after data acquisition, then we feed this model with the EMI sensing coil signals detected during the data MRI acquisition, so to predict the EMI signals presence or received by the main MRI receive coil. Then we just do the retrospective subtraction, and we found it works beautifully. Right? And then you may say, in this case, we put in around 10 EMI sensors, and the training time is used to be 10 minutes. Now it's just like 1 to 2 minutes. Go ahead.
What console are you guys using?
Oh, we're using MI solution console. It has a, yeah, that's why we choose it. It has lots of channels. Yeah, right. Okay. Also, I used to work on quite a bit. Right. Yeah. Okay. So we can get this, and we found this method is very robust. So my environment, it was noisy. I think it's noisier than the Clarissa, your scanner, because I remember when I was here, I think you or Larry told me we don't need the EMI cancellation, right? It's pretty clean, right? Because this place is quite, but in Hong Kong, it's a concrete forest, right? Noise everywhere. Sorry. Yeah. We did. Yeah, he said, did I try other adversarial network? We tried. Yeah, we tried. We found, because CNN is intrinsically convolution. It's actually mirror the transfer function frequency domain operation. That's why I choose CNN. Yeah, but later on we tried. It kind of not really working very well, but we don't see it's kind of justified, rationalized. And so we didn't spend much time because I still like physics more than computing. Yeah, so I need, yeah. Okay.
I'm sorry to interrupt, but this reminds me. So, you know, this stuff is amazing. The thing that I always worry about is running out of dynamic range in my preamp, right? So I 100% believe that these networks can reduce noise. It's fine. And I know in my lab, you know, we try to get our gain set up so that, like, you know, we get enough gain, but we still have, you know, 6 dB of headroom or something. In your lab or out in the wild, you know, it could be like 50 dB hotter in the background.
If you allow me, I will come up to that. Yeah, that's the main. I think this part you all know, right? So we found it worked beautifully with phantom data, just like us. We published, we applied, we did around 200 normal subjects, right? I found it works wonderful, say in terms of T1 weighted, T2 weighted, and flare. Oh, by the way we do flare, we don't do the traditional inversion because it will kill some signal. So what we do is to utilize the, say at the ultra low field, the T1 become much shorter for gray matter, white matter. But however, the CSF, unfortunately, is still very long, 2 seconds. Well, I think it's almost as long as the 3, you know, at the 3T. So what we did is use short TR. We just kind of suppress the CSF, right? So that give us those kind of and then we found it works well. Here's some example, and say this is we tried. This is the original one Clarissa's archive paper just published, and we were doing this. You know, we just started like we intend to enroll like 100 patients, right? And but then we suddenly had to ramp down after 20 subjects. We said we have to publish. So those are just some example. For example, this is a patient with a meningioma, right? And working with my colleague, a neurosurgeon colleague, right? And so you can nicely see it, the T1 weighted, T2 weighted, and you can see it in the DWI, nicely mirror the 3T results. Yeah, right, acquired almost the same day. And he's a patient with intraventricular cyst lesion here, large lesion here, particularly the cyst. Yeah, more or less we see the same signal trend in T1 weighted and T2 weighted and the flare and the DWI. And by the way, the DWI here is acquired by diffusion as echoplanar weighted, because I still think it is the golden sequence, right? It's extremely efficient, right? And here is a patient with head trauma. And in this case, it's a subdural effusion. And what you can see is the expanded CSF space here. You nicely see it in the T2 weighted and DWI here. So my neurosurgeon is very excited about this. They said, well, with this, I can do the on-site diagnosis. So, and here is that we also implement some more demanding sequence, such as TrueFISP. And because TrueFISP and EPI really the most efficient data acquisition sequence, right? Here we work out the field inhomogeneity issue. So you can see the T1 weight, say, well, here we don't really have a T1, we have a T2 over T1 weighting, right? And why we try this, because it's mainly contrasts efficiency is T2 over T1. Remember, T1 decreased, right? So even better, TrueFISP inside. And here also at very low field, remember the SAR is proportional to frequency squared. At ultra low field, all those problems gone. So with such extremely low SAR, we can design very fancy, sophisticated magnetization transfer pulse sequences. For example, in this case, this is sync modulated, say, block pulses, say, right? And it gives you very nice bilateral clean saturation without the sideband excitation, so that we can use it to manipulate the contrast, right? And at ultra low field and all the implant problem, you see the, those aneurysm clips, and they don't really distort the images, right? And at the ultra low field, I think this is maybe Matt, this is probably at the heart of you. I saw the paper you had. We measure the relaxivity of the standard clinical gatto. We found the relaxivity is 3 times more than that S3T. So that means if we're going to use a contrast agent, those clinical contrast agent, we don't need high dosage, right? We don't need a high dosage. And lastly, this is my favorite part. It's acoustically quiet, right? And one of my colleagues once talked to me over the lunch. He said, my wife just had a MRI scan yesterday. Guess what? She crawled out the scanner halfway. It was just too loud. Yeah, right. Yeah. So, but at this low field, like 50 millitester, even we run the DW, this is noisy sequence, I think it's still 20 dB or to 30 dB lower in terms of SPL than that at a 3T, right? So this could be potentially patient-friendly and patient-centric, right? So back to the deep learning, back from the D2 here. So what else were we doing? I think we moved the lab to a different place, and where we have a huge air duct in the ceiling. When we get there, all method failed, right? So that forced us to come up with a method within a few weeks by another talented student, and that is what we call the deep learning direct MRI signal prediction. So how does it work? Acquisition still the same. So what we do is that we use the signal, we use the MRI signal acquired here, as well as the MRI sensing coil signal acquired during this period to directly predict the EMI-free MRI signal. You may say, if we can do this, this basically will eliminate the subtraction-based procedure. They will reduce the noise amplification, right? So then you may say, how can you predict that? This is what we do. We actually take the signal here, the MRI, all the EMI signals, say detected by the MRI receive coil, EMI sensing coil, and then we synthesize, we use the EMI, we synthesize, we choose a set of arbitrary, say, EMI-free MRI signal from the high field data. Doesn't matter it's phantom or brain. And then once we have this one here, we synthesize, say, the EMI contaminated signals by adding this arbitrary MRI K-space signal to the MRI receive coil EMI signals here, And then we use this. We use a UNet to force this model predict the EMI-free signal here, where we know the ground truth, right? So with this, it works wonderfully. And we also, then you may say, well, you may have a problem here. What happened during the true FISP data acquisition? Your TR is very short and the overhead TR here is undesirable. Actually, we don't use the data here. We can use the data here to serve this purpose by using the alter case space data only where the MRI signal is minimal, right? So with this, we found it work very nicely. So we actually, we use the data, say if what happens if we have a signal acquisition window, right? And we can see that what we call the deep direct signal prediction, deep DSP method, outperforms over previous CNN method, deep learning CNN method, as well as the Clarissa's editor. Yeah, so we did try to make editor as good as could be, right? Okay. And so we also say we give this very noisy environment. We also found that, say, previously I proposed to use a large number of sensing coil. We also found that, well, this method works better when you have few sensing coils. Yeah, right. And we actually did this without the EMI signal characterization. We found something similar. So the conclusion here, well, I think it's so far this is the best method we have bumped to. So maybe Clarissa can come up with an even better one and that we can use. But I can see this going to be a continuous development. Even I don't think this method can work. You know, just in theory, if your EMI level you increase to infinite, why you think you can remove it, right? Yeah, so there's, I think there's plenty of room to make it better. And we also at the beginning, we also work with Maxim Zaitsev and just 2 to 3 weeks ago, right before the ISM deadline. And he's a hardware person, so he used his hand and actually used those existing clinical coil as the EMI sensor. He just painted on wall and had a huge signal, EMI signal generator here, basically putting a lot of noise in the. So this is probably the question. This is a 3D MRI range sequence, right? And the EMI is very strong. The MRI signal also very strong, right? So we found out that, well, this is just a 2-day trial. We found the editor method works well, and the deep DSP method also works well, but slightly better. And if so here you can see the narrow band mostly disappeared. And if I brighten the background, the broad band more or less similar among two methods. Yeah, and but this is a we will continue this. This is just a few days work during that period rush. But in terms of EMI noise level, you can see this is when the door is shut, or when the door is shut, the EMI sources all turn off. This is the case-based data. And once we have the noise here turn on, you can see this noise level is very, very high. Yeah, it's not just sporadic little EMI signals, right? So I think the challenge is that we need to continue to develop this, yeah, to make MRI truly portable without shielding, right? And so now switching topic, the next 10 minutes, I will talk about deep learning image formation for the UF MRI. And again, I think the Matt is, that's why I'm here, Matt. Every time you're a few steps ahead of the crowd. But the image quality here, this is the auto map recount of your favorite machine, and it shows the improvement, right? And this is a very short period ago. That's only 2 years ago. And subsequently, I think the Andrew Webb's group in Leiden and published in a scientific report, again, using the 2D deep learning super resolution. But the model there is very, very simple. I think it's a fast job, right? And then also, I think this is probably related to Matt too, right? Matthew Sacrani is from your lab before, and he moved to Aberdeen, and he did some 2D MRI, but this is at the 0.1 Tesla, right? This is extremity. You can see some improvement. I'm not sure it will outperform the classical BM 3D or 4D, yeah. And until like last year. And last year, I think the group, and Tyler is here, Tyler and Ignatius, I think, come up with this beautiful method, what I call 2.5D super resolution method. So what does it do? It is basically the input is T1 and T2 images with different orientation, right? Setting up a deep learning model so that it can actually, those are the, say, the ultra low field, data from the point, from the high performance system. And from those input, you can generate those beautiful MRI rich like T1 weighted images. I think this is a big step forward. I mean, I see a commentary published in Radiology. I hope all the MDs will read this paper. I think we need to kind of influence them if we can. And then in parallel, actually, we've been working on the 3D, truly 3D deep learning dual acquisition super resolution model. So I think this is, maybe I'm going to spend a minute here. The idea is to use ultra low field data set, low resolution, for example, 3 millimeter isotropic resolution. I like isotropic resolution. So we don't have to differentiate axial, coronal, sagittal, etc. Right? So we have two, and then we wanted to come up with a 3D super resolution data that has no noise, that has very little artifact, like a Gibbs artifacts. Right? So how do even some hardware artifact? How do we do that? We trained it, we built this model. This model has two layers, has three modules. First is the high order multi-dimensional feature extraction module. It's borrowed from the video world, right? The video people are very good, right? So, and the second, we do the feature fusion model. The third module is the super resolution reconstruction. And how do we train this model? Because we know the ultra low field MRI data characteristics. So we take the high field data, in this case, around the 1,000 data, whole brain data set from HCP. And from those data, we can synthesize low resolution, noisy, and artifact infected ultra low field data sets. And then we train this model with the ground truth, right? The HCP data. And then with this, we spent almost 10 months tweaking this model. And we do it on the phantom, we do it on the different subject. So finally, one day, it worked, right? It worked, and we didn't believe it, but nevertheless, this is done on the first scanner without EMI shielding. So here's the data after deep learning EMI removal. This is using the CNN, and this is data acquisition 1, this is data acquisition 2. This is the average of these two acquisition, and here is the output of super resolution model with 1.5 millimeter isotropic resolution, right? And then we take the same subject also for 3T scan. Then we do rigid co-registration so we can compare slide by slide. Not exactly, because in this case, we didn't compensate for the field gradient nonlinearity on our system. But nevertheless, here's the video I want to show. Here, this is a T1 weighted images. So what you see here, this is the raw data, acquisition 1, acquisition 2, 3 millimeter isotropic resolution, the average of two acquisitions, and this is the output of what we call a super resolution model, is with isotropic 1.5 millimeter. And here is the same subject scanned at 3T within this, the same week. Yeah, excuse me, yeah. Sorry? Oh, they are identical experimentally, except their noise are independent. Initially, we motivated by we want these two data sets compete with each other to find out the truth. Yeah, so that was the rough idea, but this otherwise is identical. They're identical, right? So I hope with this video you convinced, well, it's kind of working. I was so shocked. Right, and I thought it should work much better, but not this well. And here's T2 weighted, right? So this is a 10 minutes scan, isotropic, isotropic 1.5 millimeter synthetic resolution versus 3T. Basically, if you go this frame by frame, you can see almost so far all the features you can see here. You can see them in the 3T. Of course, not otherwise. Some of the small details here in the 3T, you cannot see them. For example, in the cerebellum, I attribute that in the cerebellum over coil SNI is too low. When it's too low, I don't expect them to be recovered, right? So with these two videos, I couldn't help ask this question that many has asked before. Is data-driven machine vision more superior than over experience-driven human vision in perceiving 3 anatomical structures, especially in presence of noise and artifacts? I think this is controversial. I just want to leave the question here. And then how do we verify this is real? This is not like an over-interpretation, auto-feeling of the missing structure. So we did a bunch of tests, and first is reproducibility test. We take the same subject out, image again, right? Of course, the head position every time different, but however, the restored structures are identical, right? And second, we did this multi-contrast. We did it for T1, we did it on T2 in the same subject. Around the same time, without moving the subject, we can see that T1, T2 weighted images like hippocampus, all those central nuclear area, their contrast, their anatomy matches perfectly as expected in normal subject, right? Yeah. And well, you may ask what happened to some abnormal, for example, Oli brain here. You can see, well, they recover very well. Because HCP data also has some very old subject, some of the patients, some of the subject has a lot of lesion. We actually use that to test, do the initial testing. And this is actually what we did is we did some patients. And in this case, well, this is a patient around 67, 69. This with a small locular infarct here. You can roughly see them here. You can roughly see them here. Say this is the super resolution recon. You can see them here as seen on the 3T, not identical, but basically it didn't fill it up, right? And here is a patient with a necrotic tumor, frontal lobe tumor. You can see it nicely. The contrast here is slightly different because those pathology tissue T2, T1 are different, right? So that's going to be the future challenge. So in this case, the T1 scan take about 10 minutes and T2 take about 10 minutes, right? Total 20 minutes. So MRI is notorious for being slow. So our goal naturally is to accelerate it. How? Finally, we figure out we don't need a dual acquisition, right? We can abandon it. And we also combine the partial Fourier sampling of the case space with this super resolution model. This will allow us to accelerate by a factor of 2. We drop the dual resolution requirement, that's give us a factor 2. So altogether, it gives us a speed of gain by factor 4. So we only need total 5 minutes to do T1 and T2 weighted 3D isotropic imaging, right? And the results, we found out this is largely similar to the method I reported earlier. Say this is in the normal brain. Largely similar. So this is we're very happy about this. Means 5 minutes. I think this is the ideal duration for MRI scan. Right? You can, with such a low cost hardware platform with computing, we can do this. That would be great. But of course, there's going to be a lot of questions about what happened when you have some pathologists your data set never seen. So we need a big data. Now I'm thinking I should buy an MRI scanner, high field. Okay, use it to generate data. So so this was published just 2 months ago in Science Advances. And actually last week, just this Nature has a commentary news on this deep road to low field MRI with high potential by 2 academic radiologists in NYU. I really like the title. The title is a subtitle, a type of MRI, it's kind of low field. They can make the technique more widely accessible, but only if image quality can be improved. They speak as a clinician. And then saying maybe the deep learning offer a deep road to that arena. So I hope this, this probably will bring more people in the field. And I also want to talk about, later on with you, how can we properly share data, get those the vision people really involved, help us, right? So, and last, I think even there's a lot of room beyond this. For example, we probably need a more intelligent image construction. construction. Why? When we put a human inside, we know what the anatomy is already, 99%. So why we acquire data as if we don't know anything, if it's a monkey brain or dinosaur egg, right? So there's so much redundant information. We've been working on this for 2 years. We couldn't figure out how. And we wrote this as an abstract with acceleration of 20, and the ISMI Society, just dump it as a regular poster, right? And I just don't understand, right? Yeah, and the other one is that, do we really need the images to do diagnosis, right? I already questioned the human vision superiority of machine vision, and last week, I visited one medical school in New York City. I asked the radiologist, how many pictures you read? I was told we read, I'm an academic resident. I read about 5,000 to 10,000 pictures every day. That's a lot of pictures. I say, don't you get bored? No, only if the cases become complicated, I enjoy it. But most of the time, cases are not that complicated, right? No. Pardon me, I need to get simple. So maybe we don't need this. A few years ago, we did a simple simulation. For example, we just need, for example, what happens if we just do the spiral scan, one line, and you cannot reconstruct a decent image. But we can train a model to see just single line, whether or not the tumor, there's a tumor or no tumor. And the simulation tells the sensitivity specificity is more than 95%. If we ask, is that big tumor or small tumor? It is a problem. Both of them drop to 91. But if you ask, where the tumor located, which quadrant, it gives you something 95. So I think there's a lot of room, but this requires a lot of data to play with, right? So with that, I'd like to conclude showing final 2 slides. I think whether or not there's a future for ultra low field brain MRI, first, I think it's hard. We have to learn new things, right? And second, but I do think there's plenty of room for computing here. And this is the early now, this is the one we just had. It's become a nicer, more open. By the way, you can be scanned and still fiddle with your iPhone here inside, right? It still works, yeah. I hope the future, before the end of this decade, something like very tiny, very, I would say, friendly and non-intimidating device like this. And I think there's a lot of room to advance this as back to what I said, affordable, patient-centric, and computer-powered point-of-care device, right? How do we do that? We have a lot of advantage. We have 50 years experience of MI engineering physics. We can keep revisiting them. And just like what Dr. Hennessy said, and he's the Google Alphabet chairman, right? And who visited my school, we had a nice chat. And he said, actually, when he talked about why Silicon Valley sustained the Moore's law for 50 years, why? He said that every year we don't have something dramatic and new, but every year we go back to what we were thinking many years ago, and we made it happen because we have a better simulation tool, we have smart people with mass training, right? So everything new probably going to be, everything old, it will become new again. So with this type of back to future through the computing, I hope the ultra low field, those little tiny machines, but the friendly machines will together with the high field system can maximize the benefit, of MRI to the common people, right? The people in the hospital, right? Yeah. So with that, I would like to acknowledge this six very talented student. One of them, she left. He left, both this is working a company and then become an academic. He stayed as assistant professor, and this 3 new students now in my lab. And lastly, thank you for your attention.